In section 4.10, we're going to be looking at something called antiderivatives. Let's start with looking at what an antiderivative is. A function capital F is an antiderivative of the function little f if the derivative of capital F is little f. So little f is the derivative of capital F. So capital F would be like a step backwards from differentiation. And of course, this must happen for all x's in the domain of little f. So let's look at some examples. If I write capital F of x is x squared, then the derivative of capital F is 2x. So for little f of x equals 2x, capital F of x is an antiderivative of little f of x. But there are other functions that are antiderivatives of little f. Let's suppose that capital G of x is x squared plus 3, then g prime of x is 2x, which is also equal to little f of x. So g of x is also an antiderivative of little f of x. So before we get going with how to find antiderivatives and what to do with them, we need to figure out what's going on and how many antiderivatives do I have. And to answer this question, we're going to go back a little bit in time and think back to section 4.4 on the mean value theorem, particularly one of the corollaries to the mean value theorem. The corollary that I'm referencing, because we had 3 of them back in that section, said that if f prime of x equals g prime of x, then f of x equals g of x plus c. Or another way to write that is that the difference, f of x minus g of x, is a constant. So what that tells me is that if I have any two functions whose derivatives match, then they can at most be off by a constant. So if we're looking at an antiderivative, if I find one antiderivative of a function, then all of the other antiderivatives of that function must be off by a constant. When we find an antiderivative of a function, what we can do is we can, instead of writing down one single function, we can write down a family of all of the functions that are an antiderivative of little f of x. F of x plus c is the family of all antiderivatives of little f. Okay, let's look at some examples. For f of x equals cosine x, find the antiderivative. Well, I know that the derivative of sine x is cosine x. So what I can do is say, okay, my antiderivative f of x will be sine of x, and we'll tack on that plus c so that we're giving all of the possible solutions, right? So the whole family of functions that are antiderivatives of little f. Let's look at another one. F of x is 5x to the fourth. Once again, I can look at this function and recognize that it's the derivative of something I know. To get an x to the fourth, when I differentiate, I lower the power by 1, so we had to start with the power 1 higher. And if I start with an x to the fifth and differentiate, a 5 comes down. So my antiderivative is going to be x to the fifth. And we include the plus c again. Identifying an antiderivative by just inspection, by spotting something and remembering what we've seen before that we could differentiate to get that, is not really a good method going forward. What we want to do is have something a little bit more robust. We want to have some rules like we did for differentiation. So we're going to introduce some rules, and at the same time, we're also going to look at some notation. In the last few examples, we used little f of x as our function and capital F as the antiderivative, but that's not really good notation. What we want to do is have something a little bit more robust, and we're going to have a special symbol for antidifferentiation. The symbol that we use doesn't seem like it makes a lot of sense at the moment, but it will in chapter 5. So we're going to introduce the notation now and use it, and I'll explain later why we use the notation that we do. For a function little f of x, we write the antiderivative as integral symbol f of x and then dx on there. We call this the indefinite integral of f. Okay, so some pieces that I want to point out. Here I have an elongated s. This is my integral symbol. And it doesn't work on its own. It needs to also have this differential with it. So just to give you something to compare it to, when we took derivatives using Leibniz notation, right, we had d dx of f, and that meant take the derivative of f. The d dx tells you to differentiate a function. It's a two-part symbol, right? We have like this fraction. And we learned in section 4.2 that we could define the differential as its own independent thing. That's going to be a connection to this dx. We'll make that connection clear in chapter 5, but for now, we'll just recognize that the way that we're going to write an antiderivative is as this indefinite integral, and it's a two-part symbol. We have the integral symbol, which is an elongated s, and we have the differential on there, which indicates the variable that we're going to use, just like Leibniz notation did for differentiation. Now, instead of calling these antiderivatives, we can call them integrals, and that means the same thing. Let's look at some rules for finding integrals. Okay, so the first thing we're going to do, let's investigate our power rule. And what I want to do is first look at the power rule for derivatives. And we'll look at how we can use the same process backwards to find a rule for integrals, which are antiderivatives. So our power rule for derivatives said that if you take the derivative of a function x to the n, then you get nx to the power of n minus 1. So the power comes down, and then we lower the power by 1. If I think about this as an equation, I could multiply both sides by 1 over n. What would be handy about that is that on the right-hand side, my n times 1 over n would cancel, and so I could look at this as just an x to a power on the right-hand side. On the left-hand side, 1 over n is a constant. It can move in and out of derivatives. That's our constant multiple rule. So I could write that the derivative of 1 over n times x to the n is x to the n minus 1. And now what I'm going to do is something a little bit strange. I'm going to relabel my variable, or my constant n here. So I'm going to think about it as being some number on the left and one smaller number on the right. Another way to imagine that is as a number on the right and a one larger number on the left. Okay, so I'm just going to replace n with n plus 1. So on the left-hand side, this would say that the derivative of 1 over n plus 1 times x to the n plus 1. If I were to follow my power rule for that, n plus 1 comes down and cancels, and then I lower the power by 1, and I'll get x to the n. But all I've done is I've replaced my n with an n plus 1 on the left, and then also on the right. An n plus 1 minus 1 just gives me an n. So looking at this, if I take the derivative of 1 over n plus 1 x to the n plus 1, I get x to the n. So going backwards, if I want to antidifferentiate x to the n, I'll get 1 over n plus 1 times x to the n plus 1. So that gives me a rule for integrals. So I can write that the integral x to the n dx is equal to x to the n plus 1 divided by n plus 1. When we write our rules for integrals, though, we want to always include the plus c. All right, now there's something that comes up here that's important, but never came up when we were differentiating. When I differentiate, when I start with something on the left, we can differentiate anything you like, and the power rule will work just fine, as long as the power is at some constant number. But going backwards, there's something that breaks down. When I take the derivative, I will never end up with a power that's negative 1. And the reason for that is when I look at my power rule for derivatives, if n is 0, when I take the derivative, when the 0 comes down, I just have 0. Everything else gets wiped out. And so in this step back here, when I multiply both sides by 1 over n, that only works if n is not equal to 0. When I replace n with n plus 1, instead of having a 0 here, I've adjusted things up by 1. So it's when this denominator is 0, or n is equal to negative 1. So we didn't have a condition for the power rule on derivatives, but we do for the power rule on integrals. it doesn't work when n is equal to -1. That seems like a little bit of a limitation, but we'll deal with that very shortly. A couple of special cases that I want to point out right away. If my n is 0, then I'm integrating a constant. So if I integrate, say, x to the 0, I add 1 to the power, divide by the new power. Well, x to the 0 plus 1 is just x to the 1 over 1, so we just get x. X to the 0, though, is just a constant. So in general, if I integrate a constant, suppose I call my constant a, then I get ax plus c. Now again, this should make sense because I know when I differentiate a constant times x, I just get that constant. So if I antidifferentiate a constant, we get an x tacked on there. All right, now let's look at some examples. Find the integral of x cubed minus 5x squared plus 3x minus 7 dx. The way that we work this is very similar to derivatives. We can treat the added and subtracted terms as separate, and we're just going to apply a power rule to each of the terms. And we can leave the constant multiples to just hang out. So when I integrate x cubed using the power rule, we add 1 to the power, divide by the new power. When I integrate x squared, we add 1 to the power, divide by the new power. When we integrate x, we add 1 to the power, divide by the new power. And for constants on their own, when we integrate them, we get an x that gets tacked on. And then, of course, at the end, we add in our constant c. And that's basically it. Like, there's no simplifying I can do here. I can rewrite this to make it look a little bit nicer. So I have 1/4 x to the 4th minus 5/3 x cubed plus 3/2 x squared minus 7x plus c. And that's it. Look at some other integration rules. In general, every time that we can come up with a rule for derivatives, we can come up with a corresponding rule for integrals. Some of those work very well. So let's start with those first. The derivative of natural log of x is 1 over x. If I take the derivative of the natural log of the opposite of x, using the chain rule, I get 1 over the inside stuff times the derivative of the inside stuff is also 1 over x. So whether I start with x or I start with the opposite of x, I get the same result. The thing I do have to be careful about is that in this first one, in order for natural log of x to make sense, x has to be strictly greater than 0. In the second one, in order for natural log of the opposite of x to make sense, x has to be negative so that the opposite of x will be positive. So although these two give me different formula, or two different functions when differentiated give me the same formula, they don't overlap at all in their domains, so I don't have a problem here. What we can do instead is we can combine these together. We can say, oh, here I have x when x is positive, and the opposite of x when x is negative. That's what the absolute value function is. The absolute value of x is x if x is greater than or equal to 0. The opposite of x if x is less than 0. What I really have is a differentiation formula for the natural log of the absolute value of x. And that is 1 over x. So as an integration formula, when we integrate 1 over x dx, what we want to do is maintain as big a domain as we possibly can. And so when we write our answer, we're going to use the absolute value of x instead of just an ln of x. We have a few more easy ones. I know the derivative of e to the x is e to the x, so the antiderivative of e to the x dx is e to the x with my plus c on there. Okay, so some derivative rules that we have to be careful about. The product rule. The product rule says that if I take the derivative of f times g, I get f prime g plus fg prime. Trying that backwards would be really tricky. If I started with something that looked exactly like this, the derivative of one function times the other, plus the first times the derivative of the second, if I had this exact thing and I antidifferentiated, then that's fine. I could write that as f times g, but that's not typically a realistic expectation to ever run into. And even if I did, I probably wouldn't recognize it. So there's not a good way to antidifferentiate a product. Okay, so we don't have an integration or antidifferentiation rule for products. Now there is something kind of like this. There is a rule that you'll learn about in Calculus 2, but it's not so much an integration rule as it is a procedure. So similar to L'Hopital's rule takes one limit and it turns it into another limit. It doesn't really solve my limit problem, but hopefully it makes it easier to work out a second limit. The rule that you learn about in Calculus 2 is integration by parts. It takes an integral and turns it into a different integral, and it does indeed work on products. Okay. For right now, we're just going to say we don't have one for products. That process is complicated, and there's a lot of subtlety there that you need to be careful about. So right now, we're just going to say don't do it. Similarly, the quotient rule, that said if I take the derivative of f over g, we had f prime g minus f g prime all over g squared. This doesn't work well backwards either. Okay, so we don't have a corresponding antidifferentiation rule for quotients. Okay, I'm going to stay quiet about the chain rule for now because we are going to learn a way to antidifferentiate a chain rule. It's a process known as U substitution. We'll learn it in Chapter 5. So we're just going to stay quiet about it for now, and we'll learn that later. So now what I want to do is look at some examples of how do I actually find an antiderivative of a product or a quotient now that I know I don't have a product rule or a quotient rule. So here's our first example. Integrate tangent x times secant x dx. So not only do I have a product, but I have trig functions. The key here is to recognize that tangent x times secant x is the end result of differentiating something that we know. So this gets back to a basic rule where I can say, oh, if I know a derivative, I can think about that backwards as an integration rule. So if I think of the derivatives of the different trig functions, let's make a little table of trig functions and their derivatives. So if I start with sine x, the derivative is cosine x. If I start with cosine x, then the derivative is negative sine x. If I start with tangent x, the derivative is secant squared x. If I start with secant x, the derivative is secant x tangent x. If I start with cotangent x, the derivative is negative cosecant squared x. If I start with cosecant x, then the derivative is negative cosecant x cotangent x. I can turn those into antiderivative rules. So if I start with cosine x, that comes from differentiating sine x, so I'll get sine x plus c. If I start with just sine x, if I take the derivative of cosine x, when I differentiate, I get a negative. So if I start without a negative on there, or another way to think about that is if I start with a double negative, I'll take one away. So we have negative cosine x plus c. If I start with a secant squared x, antidifferentiate, I'll get tangent x plus c, just following my rule directly. Similarly with secant x times tangent x, when I antidifferentiate, I'll get secant x plus c. If I start with a positive cosecant squared x, when I antidifferentiate, I'll get a negative cotangent x plus c. And likewise, if I start with a positive cosecant x cotangent x, when I antidifferentiate, I will get a negative cosecant squared. Sorry, not squared. I will get a negative cosecant x plus c. Coming back up here, when I see that tangent x times secant x, I can say, all right, when I antidifferentiate that, I'm just going to get secant x plus c. Okay, let's look at another example, this time with quotient. So here I have x squared minus 3x plus 4 all over x dx. What I want to do is, before I start antidifferentiating, I want to rewrite this so that I don't have a quotient. So what I'm going to do is break this up into 3 separate fractions. X squared over x plus negative 3x over x plus 4 over x. And when I simplify, x squared over x gives me x. Negative 3x over x will just give me a minus 3. And then the 4 over x, I kind of want to leave, I'll maybe pull out the constant. What I really want to do is just put this in the right form for anti-differentiating. The 1 over x is the right form because I want to look at that and say, oh, that gives me a logarithm. I'm not going to use the power rule there. For the other two, I am going to use the power rule. So when I use the power rule on x, I get x squared over 2. For a constant, we tack an x on. The 4 hangs out, and when I anti-differentiate 1 over x, we get the natural log of the absolute value of x. So when we run into a quotient, the idea is that we need to get rid of the quotient. Okay, we're going to do a few more examples, but I want to do them in another context. Let's look at solving initial value problems. So let's first look at what an initial value problem looks like. The idea is that instead of starting off with a function and then finding its derivative, I want to start off with a derivative and recover the original function. That's a lot like what we've been doing up until this point, with one slight difference. So let's look at an example, and I'll walk you through. So let's suppose that I'm told that the derivative of a function is 3x squared minus 4, and I'm also told that f of 0 is 7, and I'm asked to find f of x. Well, I know that if I start off with a derivative, that I can anti-differentiate to get the function back. So f of x is the antiderivative, or indefinite integral, of 3x squared minus 4 dx. So let's go ahead and anti-differentiate. The 3 hangs out. When I anti-differentiate x squared, I'm going to get x cubed over 3. Tack an x onto the constant, and we always put in our plus c. The 3's will cancel. And normally we would say, okay, I'm done. I have my family of functions whose derivative is 3x squared minus 4. But when I think about an application, what I've written here are infinitely many functions that don't overlap with each other. And if I'm solving a specific application, there's probably just one function that I'm interested in that actually models what's going on. And that's what this extra piece of information is for. If I have one more piece of information, I can know which function I'm dealing with. So we're going to use this extra piece of information to solve for the c. So our step 1 was to find f of x using an integral. Our next step is going to be to find the constant c. And we're going to use what we call the initial condition for that. So this is our initial condition. Why do we call it that? Well, in this example, if I plug in 0 and get a number, you could think of if my domain was time, if this was a function of time, then at time 0, that would be when things start. So f of 0 equals something is my initial condition. This is what's going on when things start. And this is kind of a common initial condition for these types of problems, and that's where this gets its name. Calculus has a lot of roots in physics. Isaac Newton was a physicist, and so a lot of the early problems were based on physics problems, and that's where a lot of the naming came in. All right, so let's look at the second part now. F of 0 equals 7. So when I plug 0 into my function, I know that's going to output 7. 0 cubed is 0, minus 4 times 0 is 0, so we just end up with c equals 7. So the specific function that I want is x cubed minus 4x plus 7. So this is the solution to my initial value problem. Let's look at another example. Suppose that f prime of x is equal to square root of x plus x squared, and f of 0 is 2. Let's find the function f of x. So once again, I'm going to start by anti-differentiating. I'm going to rewrite the square root of x as x to the 1/2 power. Then it's easier to see how to use the power rule. And I add 1 to the power. 1/2 plus 1 is 3/2. I want to divide by that new power. Now, a trick that I like to do that is really common, dividing by this power will be dividing by a fraction. That means I have a fraction within a fraction, and I don't like that. But dividing by a fraction is the same as multiplying by its reciprocal. So I like to just multiply by its reciprocal from the beginning. We do the same thing with the second one. When I add 1 to the power, I get 3. Instead of dividing by 3, we could multiply by 1/3. It's just a different way of writing the same thing. Now let's use our initial condition. F of 0 equals 2. So 2/3 times 0 to the 3/2 plus 1/3 times 0 cubed plus c equals 2. 0 to the 3/2 is 0. 0 cubed is 0. So we get that c is 2. So the f of x that we're looking for is 2/3 x to the 3/2 plus 1/3 x cubed plus 2. Okay, let's look at one more example. The car is traveling at a rate of 88 feet per second, which for reference is about 60 miles per hour, when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second squared. How many seconds elapse before the car stops, and how far does the car travel during that time? So what we're going to do here is try to model the situation. To begin with, I want to remember the relationship between functions and derivatives. And when we first started talking about derivatives, we said if I look at the position of an object or a particle, or in this case a car, then the derivative is going to tell me velocity, and the second derivative is acceleration. So going the other way, if I start with f of t is the position of the car, and f prime of t is going to be the velocity, and f double prime of t is the acceleration. Well, what do I know in this problem? The second sentence says that the car begins decelerating at a constant rate of 15 feet per second squared. So my acceleration is a constant. So that tells me that f double prime of t is equal to 15, except that it's decelerating, right? So the velocity is going down over time. So that second derivative is actually negative. Then what else do I know? Well, I know that the car is traveling at a rate of 88 feet per second when the brakes are applied. So if I think of time 0 as being when we hit the brake, then f prime of 0 is going to be 88. If we try to rephrase that first question, how many seconds elapse before the car stops, what we want to do is find t when the velocity, which is f prime, is equal to 0. So let's start there. Let's see if we can figure that out. So if I want to find f prime of t, we're going to take the antiderivative of f double prime of t. So I write down my indefinite integral, negative 15. And I'm using dt now instead of dx because my variable is t, not x. So I get negative 15 t plus constant c. So that's my velocity function. I know that at time 0 the velocity is 88. So negative 15 times 0 plus c equals 88. So c is 88. And that means that f prime of t we could write as negative 15t plus 88. Good. Now I want to find t when f prime of t is equal to 0. So now we need to solve f prime of t equals 0. So negative 15t plus 88 is equal to 0. I subtract 88 on both sides, so negative 15t equals negative 88, and then divide both sides by negative 15. Since this is somewhat of an applied problem, rather than leave my answer as a fraction, I would like to have a sense for what's going on. So I'm going to write this down as a rounded decimal, and I get 5.8667 seconds, which is the answer to the first part of the problem. Now let's look at the second part of the problem. How far does the car travel during that time? That's tricky because the speed the car is moving is changing over that time. So we can't just say, oh, it's going this speed, multiply by this amount of time, and you're done. What we need to do is look at where does it start and where does it end. So let's find the position function. So we're going to find the position function f of t. F of t is the indefinite integral of f prime, which we found earlier was negative 15t plus 88. So we use our power rule for integrals. The negative 15 hangs out. Antidifferentiate t, I get t squared over 2. When I antidifferentiate a constant, the t tacked on, and then we have plus c at the end. Now we're a little bit stuck because I have a plus c, but I don't have another initial condition to solve for my constant. So we have to look back at the context of the problem and see if we can figure that out. I want to know how far the car traveled. What we can do is we can say that at time 0, it's at a starting place, which we'll just label as 0. I'm not really too worried about the position function as what it's measuring. What I really want is a difference in the position. I want to know how far do we move from the start to the end. So it doesn't really matter what we call our starting spot. I'm just going to label it as being 0. So f of 0 is 0 plus 0 plus c, and that's equal to 0, so c is 0. So my position function, f of t, is negative 15 halves t squared plus 88t. And I want to know how far the car traveled in 5.8667 seconds, so I can find the position there. Plugging in, I get 258.1333. The units that we had from the beginning were in feet and seconds, so our distance measure is going to be in feet. Since we start at position 0 and we end at position 258.1333, we travel a distance of 258.133 feet. And that's how we solve initial value problems.